Hello, everybody. All right, so we are moving on to section 2.2, which is more on functions and their graphs. So, what we're going to focus on in this one here is we're going to look at identifying intervals where we're going to increase, decrease, or be constant. We're going to look at graphs and locate their relative maxima and minima. And then we're going to identify if it's going to be an odd or even function and even recognize some of their symmetries. After that, we're going to understand and use piecewise functions. And then finally, the funnest one of all is the find and simplify a function's different quotient. Okay, so we are going to start off with the first two. So we're going to look at increasing, decreasing, and constant. And then we're going to look at locating the relative minimum and maxima. So when we have a function, what we're going to do is we need to figure out on intervals of where I'm going to increase or decrease, or where I'm just going to be straight across and be constant. So you know a function's going to be increasing when your x's increase and your y's increase. So your x's are always going to be increasing and your y's will always increase. So as long as that is always true, as you read left to right, then you are going to have an increase function. For decreasing again, as you read from left to right, your y values are not increasing, they are actually decreasing. So you can kind of see here your y values are actually what are going to drive the whole entire function to make your graph either increase or decrease or even be constant. So you're really looking at those y values and in order from reading left to right for your x values. And if your y values are increasing, that portion is increasing. And if your y values are decreasing, then that portion is decreasing. You know you are constant, again, when you read from left to right, or any x value on that interval, if all your y values are exactly the same, then you have a constant, which means you have a horizontal line. So constant basically means you have a horizontal line. Increasing means you have a positive slope, and decreasing means you have a negative slope. So that's how you're going to kind of determine exactly what you need to be focusing on when you do these is by looking at that. Now, on some of these, what we're going to have you do is you might actually have to prove that it's increasing, decreasing, or constant. And so in order to be able to do that, you need to remember this formula right here. y2 minus y1 over x2 minus x1. So when you look at this and if they say, okay, am I increasing, decreasing, or constant over this interval, you are literally going to use the slope formula to be able to prove that. And all you do is you plug in the first endpoint and you plug in the second endpoint. And when you do that, you will either get a 0 for constant, a positive number, which means you're increasing, or a negative number, which means you're decreasing. Those are the only three options you're going to have on this. Well, I guess there's kind of a fourth one. Your denominator could equal 0, but that's a whole different topic because we're not working on that right now. We're working on increasing, decreasing, or being constant. So when we talk about this piece right here, you'll look over an interval, or the other thing that you might have to look at is you might have to pick a point somewhere on the graph that you're looking at and the turn point. So you look at your turn point and then a point either before or after that turn point, or not of, before or after. Because what's going to happen is, let's say you have this graph that looks something kind of like that, okay? If I want to know where am I decreasing at, and I want you to prove it, so what you would look at is just say, okay, well, I know I'm increasing here. And I know this because as my x's are getting bigger, my y's are getting bigger. Sorry. And then so something happens here when I turn on this turn point. As my x's get bigger, my y's are getting smaller. And then when I get to here, I'm looking at this turn point and doing the same thing. So what's going to happen is you're going to figure out this is my x1, y1, and this would be my x2, y2. And what you would do is you would plug it back into the slope formula here, and it's going to give you a negative number. And that's all you need. I don't need to know the actual number or anything else. I just need to know if it's positive, negative, or zero to determine if it's going to be a constant, increasing or decreasing. Okay, so if they don't give you the interval and then ask you to prove that you're increasing over these intervals, that's what it's going to say. Now, here you're bounded, but what happens if you're looking at over in this area, if you're going to be increasing or decreasing or not? The same thing. So you're going to pick this point right here because that's your turn point, and then just pick a point over here, like that point right there, and you'll make that your y2, and then or x2, y2, and then you plug it into the slope formula, and then you'll wind up with a positive number. So those are the two things that you need to remember when you're going into this, that, if you're bounded, you're going to be looking at between the two turn points. Otherwise, you're going to pick a point somewhere, towards the bottom, I guess it's up to you, on the what looks to be the increasing portion of the graph and that turn point, and you'll see that you're actually going to be increasing for this graph here, increasing there, you're decreasing here, and then again, if you pick that point there, it'll show that you're increasing here. Okay. So the other thing, when we're talking about increasing, decreasing, a constant, we also talk about minimum and maximum points. And so the specific thing that you need to know here is at turn points, you will have either a minimum or a maximum value. And so this is how you know if what your turn point is. If you come from a positive slope and you turn and you go to a negative slope, you have a max point. If you come from a negative slope and turn and go to a positive slope, you have a minimum point. And again, if they ask you to prove, that this is a min or max point, again, you go back, you look at your slope or whatever else, you pick something before it, you use that actual turn point. So like, for instance, here, you would actually use this point, and like that point here, you'll get your positive answer. You'll use this point and this point right here, and you'll get your negative answer. And then that proves it, because this x1 value and this x2 value here, as it's increasing, I increase, turn, and then decrease. And the same is true over here for the minimum. You'll use that point here, and then you'll pick a point and use that point here, and then you'll pick a point, and then it'll prove that it's going to be a minimum. And again, using the same x1 going to x2, that same process here will show that at x1 I'm decreasing to this turn point, and then when I go towards x2 I'm increasing. So again, when it asks you to approve it, that's what it's looking for. When we talk about minimum and maximum, we have what's called a relative minimum. What that basically says is there's an open interval, so we're not bounded, or we could be bounded, but if we're not bounded or whatever, it's just saying you have a relative maximum. If you have basically that positive slope to a negative slope turn points there, and you have a relative minimum at the same thing. Now, you'll hear these words relative min, relative max. What this basically means is that you could have more than one min and max. Each turn point will either be a minimum or a maximum. They will all be relatives except for one, possibly. Okay, there are occasions, especially in a sine wave, which we'll learn later on, that you will have no absolute maxes and no absolute minimums. Absolute means there is only one absolute 100%. It's the highest point of this graph or the lowest point of this graph. So you'll only have at most one absolute max and at most one absolute min. It's either a 0 or a 1. You can have as many relatives as you want when you're actually trying to graph. So if I gave you something that looks a little like this, so we are here, and let's not be on that one, let's be on this one here. And so we're coming in, and then we're going to turn here, then I'm going to turn here, and then I'm going to go out. Okay, so if I'm looking at this, I've got turn points that are here, 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 and here. Now, I tried to make these two right here be pretty much the same thing. I kind of did a good job, but I'm not really sure. But we're going to pretend that they're actually both the same bottom y value. So it'll be about that value right there. So if I'm looking at this, you know that I'm going to be increasing from here, decreasing here, increasing here, decreasing here, and increasing here. So we know that here is a max, here is a min, here is a max, here is a min. Now, the key is here, so see these two minimums who are supposed to be the same y value, just to let you know, okay, I'm not an artist, but these two are supposed to be y values that are the same thing. So these two here we call a relative. Ooh, that was bad spelling. Hold on, let's try that again. Not relative. Relative min. And it's relative because there's not an absolute. I have two minimum values here. So as I was saying, they're relative because there's not an absolute y value that's lower than the other. Because of that, I've got two minimum values here. But my max values, as I'm looking at my max values, I've got one max value that's higher than the other in terms of my y values. So this one here would be my absolute, as this one here would just be another relative. I told you, you can have as many relatives as you want. But you can only have the one absolute. And so you can see that this one's clearly higher than the other one. And because of that, you your maximum here is going to be an absolute, and this one's going to be considered a relative. So let's take a look at some of these. So we're going to focus first off on the intervals. So state the intervals on which which the given function is increasing, decreasing, or constant. So the first thing we want to do is we want to identify these turn points. So we got a turn point that's right here and a turn point that's right here. And by looking at the graph, we can see, because we don't have a function here, so we just have to look, we can see as my x's are getting bigger, my y's are getting bigger. So I'm increasing here. As I turn and get to here, as my x's are getting bigger, my y's are going to get smaller. And then as I turn again, as my x's get bigger, my y's get bigger. So I'm going to be increasing from negative infinity to my first turn point, which is -1, and I stop. Because then I'm going to turn and I'm going to start at -1 and I'm going to decrease until I get to a +1, and then I stop. And so then I come back up here and then I go, okay, I'm going to start back up at that 1, and then I'm going to keep on going to infinity, and then I stop. Okay. So when you go through these, notice I didn't use any brackets here at all. Even though they're included, these numbers are included at a turn point because one is actually not in like, let's see this what it says. So like here on this first increase, I go up to -1. Well, -1 shows up here and here. So a turn point actually doesn't actually start in that specific interval. You start at that, but you don't include that actual -1 because that -1 is a max or a min. You don't deal with that. You just use it in terms of a parenthesis versus a bracket because we are not actually including that because it's included here and here, and you can't be in two places at once. So you can't be increasing and decreasing. So something special is happening there. So therefore, when we write our intervals, we write them with parentheses versus brackets. Even though that number truly does exist, it just can't show up in two different spots. Okay. All right. Let's try one more. So again, intervals of increase and decrease. I'm looking at this. So as my x's are increasing here, my y's are decreasing to about right there. So there's my turn point. So I'm decreasing. I turn, and then I am, as my x's get bigger, my y's are going to increase. So that means for my increasing, I come from negative infinity still, because remember, x values. So when you're dealing with these, it's always x values, never your y values. So I'm going to go all the way up to, that looks like the number 3. And then I turn. And then from 3, I'm going to go off into positive infinity. Okay. So again, when we deal with functions, we only deal with the x values themselves. We do not deal with anything else. All right. So I'm going to give you a few moments. I want you to hit the pause button, and I want you to identify the intervals because this one's a little different. The intervals of increase, decrease, and this one's got a constant in it. Now, the difference is, before I turn you loose, notice how here I went off into infinity and everything else. But here I've got these closed dots, and then this one over here actually goes off into infinity. So I want you to take a few moments and label where you're increasing, decreasing, and constant at, and then we'll check your answers. Okay? Ready, set, pause. All right. Welcome back. Let's see how you did. All right, so I'm going to be increasing. I'm going to start at -2, and I'm going to go all the way up to a -1. But whoa, wait. You said earlier, or I said earlier, that you can't use a parenthesis. Well, notice that this -2 is, or it's not in a parenthesis, a bracket. That -2 is not sharing with anybody else. It is a standalone point because it doesn't have anything over here or over here that it has to deal with. It's only specifically by itself. So it's the start point. So yes, you can have a bracket for this. Now, if I would have had something going off and say into that direction like that, then no, that would have been a parenthesis instead. But because it's where I'm starting at, I'm good to go. I don't have to worry about bringing in anything else. So notice here, I'm at -1. So at this -1, it looks like I'm going constant straight across. I have no slope at all. So I'm constant from -1 to 1, and then I turn. Well, if I take a look here, I turn and I'm going to decrease. So I'm going to start here at 1, and I'm going to decrease all the way down to 3. And then I'm going to turn again, and I'm going to start back up at 3, and I'm going to run off into positive infinity. So this is what I'm looking for when I'm talking about increasing and decreasing and constant. Okay. So now I'm looking for maximum and minimum. So you're going to look at this graph, and we're going to determine where is this maximum and minima. So what you're looking for is, remember, maximum, you're coming from a positive slope to a negative slope. And minima, you're coming off of a negative slope and you're going towards a positive slope. So if you look at this, you see you got a turn point here and a turn point here. So you know you've got a minimum and a maximum that you are dealing with. So if you take the look at this first one, I'm coming from a positive slope and I'm turning and going negative. So I've got a maximum point at x is equal to negative 1. Once I've turned, I'm coming from a negative slope to a positive slope, so now I have a minimum. I have a minimum at x equals 1. Okay? These, yes, they're called relative. The reason they're called relative in this case here is because this is going off into infinity. However, if this had been bounded, whereas you have specific endpoints, let's say like right here and right here, this would be, both of these would be called an absolute max and an absolute min because there's only one of each. So relative usually happen here. Then we can look at the localized piece, which is what this is right here. This is considered localized because this is the only thing that the graph is getting type of shape to. And then you can look at there and then determine minimum and maximum points from the local piece. Okay. All right. So let's talk about symmetry and even and odd functions. So when we deal with even and odd functions, some of this you've seen before, some of this might be kind of new, but let's talk about what an even and odd function is. Algebraically, an even function is when you take a function and everywhere you see an x, you put in a negative x, and then you get your original function back. So if you can ever just plug in like a negative x everywhere you see an x and get that actual function back, you have an even function. So basically what happens is nothing really changes. So an even function, just a really basic one, looks something along the lines of your parabola. Okay, so a parabola would be considered an even function only if it's the y-axis that splits it. Okay, so your y-axis actually has to split your function in order for this to be considered an even function. Because when we talk about even and odd, we are talking about symmetry, how the graph is actually symmetric or not. Okay. When we deal with odd functions, and this is algebraically, I'm going to show you how to do it graphically here in a moment. If you take that same negative x value that you plugged in here and everything got a sign change, then you have what's called an odd function, because an odd function changes its sign if x is replaced with negative x. So that means everything in that function will get a sign change. So with that, let's take a look at this. When we deal with an even, so this is graphically, so when we're dealing with an even function, this is what you have to remember, and this is the most important piece. An even function, you are split right down the middle with the y-axis. Okay, as long as this happens and half of your graph is on this side of the x-axis and the other half is on this side and you're equal distance and everything else, you have an even function. If that same, let's pretend that you had a graph that's over here and it's being drawn like this, okay? Yes, it does look like it would be an even function. However, it is not an even function because what splits it down the middle is not the y-axis. It has to be the y-axis in order for it to be considered an even function. So just because it looks like it doesn't necessarily mean this is the only way that your graph is going to really look. It's going to be probably in a U-shaped of some way, shape, or form. If we're talking about an odd function and you're sitting here looking at it, so this is an example of an odd function. Here's the easiest way to do it. So first off, an odd function is your reflective over the origin, which means that this side, if you took this side of the paper and you flipped it over here, then this piece would match up perfectly with this piece. However, these things are in your calculator or whatever else, so there's got to be an easier way, right? Well, the answer is yes. If you take your calculator and you graph it, and then you say, okay, calculator, we're going to see if you're odd or even, or well, we're going to see if you're odd because that's what we're focusing on. If you take your calculator and you flip this upside down just like that, If you get the exact same graph back, you have an odd function. So if you're looking at this, notice down here, I flipped this graph upside down. I have the same graph. So therefore, this would be considered an odd function. So if you're not sure and the algebraic piece is just not coming out the way you want it to, throw it into the calculator and see which one is, if it's going to be odd or even. Because if it's not odd and if it's not even, it's going to be considered neither. Okay. So we have this problem here. We need to identify if this is odd or even or neither. So very first thing we're going to do is we're going to say, okay, my h of negative x, and this is going to equal negative x to the fifth plus 1. So now I've got this, and I come over here and say, okay, well, negative x to the fifth gives me negative x to the fifth plus 1. So I did not get a sign change on everybody, because in order for it to be odd, I need it to look, oops, not like that. I was trying to evaluate it for negative 1. I need this to look like negative x to the fifth minus 1. That's what I need it to look like in order for it to be considered odd. But if you notice here, when I plugged in that negative x, the only thing that got the sign change was the x value itself, and that other constant number didn't move or didn't change. We know it's not even because, again, when I plugged in the negative x, I didn't get back the original equation, because if it had been even, if I plugged in negative, I would have gotten this piece back. Well, I didn't get that back, and I didn't get a whole entire sign change, so this answer would be neither odd nor even. So you don't get an odd and you don't get an even graph on this one. Okay. So let's try this one more time. Let's say g of x is equal to x to the fourth minus 2x squared. So what I'm going to do is come over here and say g of negative x. And so I've got negative x to the fourth minus 2 times negative x squared. Negative x to the fourth is still x to the fourth minus 2 negative x squared will be x squared. I get the same thing back. So this and this match, and because they match, I wind up with an even function. Okay. So now I want you to try one. So take a few moments. I want you to pause the video, and I want you to tell me, is this even? Is this odd? Or is this neither? And pause. All right. Welcome back. So let's see how you did. So I plug in my negative x. So I get negative x to the third minus 6 to the negative x. So this winds up being negative x to the third. So negative 6 times a negative x gives me a positive 6x. Everything got a sign change on this one. And since everything got a sign change, this function is going to be considered odd. Okay? So those are the three things that you're going to see. Even, I got the same exact thing back. Neither, this is going to be the most common answer that you get. Neither will be your most common answer because the majority of functions out there are not symmetric about the y-axis, and they're not symmetric about the origin. So because of that, you're going to have a lot of neither answers, and that's okay. Put it into your calculator to make sure and that you've done everything correctly. All right. So then, now we have piecewise functions. Okay. Piecewise functions, that's where we have more than one function here, and we have some boundaries that's attached to them. So then when we go through this and we do a piecewise function, what we want to do is we want to follow the rules that it gives us and just kind of like, I think the first part of this is going to be evaluating. So you have this piecewise function. You have boundaries in your piecewise function. So this tells you your boundary. And if your value that you're looking at fits this boundary, then you'll use this equation. This boundary here is the other one because this is a piecewise. So if your number that you're going to be given is greater than that 60, then you use this equation to evaluate. So I'm going to look at the first one. Find C of 40. Well, my 40 falls in between 0 to 60. So that means there's nothing here. So basically what it's looking like is I have this very constant line all the way to 60. When I get to 60, something happens. So that means at 40, my answer is just going to be a 20 because there's nothing to evaluate. It's just one of those, it is what it is, okay? When I'm looking at the 80 is greater than 60, so it matches this boundary here. So then I'm going to take this 80 and I'm going to plug it in. So 20 plus 0.4 times 80 minus 60. So 20 plus 0.4 times 20. So I get 20 plus 0.4 times 20 is 8. So I get 28 as my answer. So when I'm looking at this 80, I wind up with a 28. Okay. Piecewise functions are extremely easy. You just got to look at the boundaries themselves. Okay. But just keep that in mind. So the other thing it's going to have you do is graph these things. Now, your calculator is not so nice about this. So what you have to do is you have to literally piece this stuff together. That's one of the reasons why it's called a piecewise, because you are piecing stuff together. So we know that with this piecewise function here that they've given us, we know we have a constant line at 3 as long as my x is less than or equal to -1. So I've got something that's going to happen like this, and then when I get to -1, then we jump down to here. And then from here, everything that's bigger than -1, I'm going to use this one here. So when you evaluate this to put this together, you actually still have to evaluate this piece here, even though the -1's included up here on this one. And the only reason is because you're going to have an open dot. You're going to have an open dot on this one at -1, and you have a closed dot on this one at that -1. So when you have your graph, when you have your graph here, you'll have an open dot, and then you're going to run off and do something like that in that direction. So let's actually put this on a grid and take a look at this. So again, here is some ordered pairs just so you can see. So f of x is equal to 3. So you see this one, you see that one, you see that one. So you wind up with this set of ordered pairs. Then you're going to plot those points. And then x minus 2, again, you're going to use -1 and greater. And so you're going to plot those points, remembering that this point here is an open dot and that this point here is your closed dot. Because remember, wrong spot. My -1 here is included in this. So we're including that -1 right here. Okay. So then you come over here to your graph and you literally just plot your points on this. Maybe if I can find it. Oh, there it is. Okay. So there is my first part from -infinity up to -1. And notice there's a closed dot right there. And then I pick up down here with my open dot and I run off into that direction there. Okay. So when it's asking for piecewise, your calculator won't do this. It won't like you too much. So you're just going to have to take a look at it, focusing on the boundary restriction that it's telling you, which like on this one, this is the boundary restriction that you're looking at right here is that -1. Okay. with that being said, I wonder if I can pull this up. There we go. There we go. So if I'm looking at this, I'll just kind of walk you through it so you know what to do. Maybe. So I have a 3, and then I have an x minus 2, and then make sure I'm in my standard. So there's that, and there's that. So now we know what my graph is going to look like. What we want to do is we kind of want to hone this in a little bit so we can kind of get a better glimpse of what I'm actually going to be focusing on. So I've got this happening here. So now I'm going to come over here so I can write on this for you. I'm going to look at this piece here. Let's copy and edit. Stick that into here. Edit and paste. So now that I'm looking at this, so this is what your screen will look like, sort of. And so here at this -1 piece that's right here, you know you're going to have a closed dot here and an open dot right here. On this one here, I don't care about any of that. I don't care about any of that. All I care about is this piece going in that direction. On this one, I don't care about any of this. All I care about is going in that direction. So that's one of the ways that you can kind of focus on your piecewise in that direction as well. So you can kind of see what you need to get done. Okay. All right. So that is piecewise for graphing. Now onto the fun one, the difference quotient. The difference quotient is a lot of algebra, so I don't want to scare you, but this is what the difference quotient is. So what we're going to do, it's basically when we get into, there's another section that we're going to be getting to here shortly that's called average rate of change, and you need the difference quotient in order to do the average rate of change. So what we're going to do is we're going to go ahead and take these functions that they're going to give us, and we're going to simplify this down using the difference quotient. And so your difference quotient looks like this. So you have f of x plus h minus the actual function itself in this whole thing over h. Now, if this is done correctly, okay, if you do everything correctly, then you're going to wind up with this back piece back here canceling with a lot of the things here in the front, and you should be left with everything in your numerator should have an h in it, and your denominator should only be an h. That way you can go through and cancel things out. So that's the key piece you need to keep in mind as you do this difference quotient. The goal is to get rid of all your singular x's and your constants on the top, so that way you're left with nothing but h's, so that way you can go through and cancel stuff out. This is kind of a long process, so keep this in mind as well. So don't start this if you have a little bit left on your notes page. Go to a new page. So we are going to take this and we're going to apply the difference quotient to it and simplify. So there we go. So this is what we're going to do. So we're going to take this piece. So here's my f of x. So go ahead and let's figure out what is f of x plus h. We're going to go ahead and figure this out. So we're going to walk this down in steps. So everywhere I see an x, I plug in x plus h. So I'll plug another one into here. Okay. So that's the first step that we're going to do. Now we're going to clean this up. So it gives me -2 times x squared plus 2xh plus h squared, and then plus x plus h plus 5. I'm going to keep cleaning this up so I can't do this no more. So -2x squared minus 4xh minus 2h squared plus x plus h plus 5. There is nothing for me to be able to combine here, so I can technically leave this alone for right now. So now, we did the first piece, the f of x plus h. Now we're going to take this answer here. Again, we're going to walk this down into steps so you can see what's happening. So we're going to take this answer, and then we're going to subtract f of x from this. So I'm just going to rewrite this whole entire line here. Minus 2h squared plus x plus h plus 5. And then what I'm going to do is I'm going to say minus this whole thing right here. So negative 2x squared plus x plus 5. Okay? Now I'm going to clean this up because we like to clean things around here. So this gives me negative 2x squared minus 4xh minus 2h squared. Told you this is a lot of algebra. Plus x plus h plus 5 plus 2x squared minus x minus 5. So if you did this correctly, anything that doesn't have an h should cancel out. So this negative 2x squared is canceling with that 2x squared. This x is canceling with that negative x. And this 5 is canceling with that negative 5. So if done correctly, everything that you write should have at least one h in it. Oops. So mine are negative 4xh minus 2h squared plus h. Okay? This is a good thing because everything that we're left with has an h in it. So now we're going to come over here and say, okay, f of x plus h minus f of x. Now we're going to go all over h. So I'm going to take this line right here, and I'm going to write it there. And then I'm going to divide everything by an h. So now everything is divisible by an h. So if I look at this, I'm going to break it down just so you can see this. Normally I wouldn't do this, but I'm going to go ahead and do it just so you can see what's happening here, so you don't get confused. But this is really what you are looking at. Okay? So taking this really big fraction, and I'm going to divide it down into 3 smaller fractions, so each term gets an h. And then I'm going to clean up each term. So this h and that h cancels. This h and one of those cancel. And this just goes to a 1. So when I write my final answer, I have negative 4x minus 2h and plus 1. That is what my difference quotient gives me. It gives me this right here, and you are finished. I know it's a lot, but this is what we are looking for as your final answer right here. Okay? So now what I want you to do, yep, you guessed it, you have one to try. You're going to use the difference quotient to simplify this piece right here. F of x is equal to 2x squared minus x plus 3. So I want you to go through the process, go through the steps, and break it all the way down. And let's see how you did. Okay, so go ahead and hit the pause button now. All right, well, welcome back. Let's see how you did. So we have our difference quotient here. Okay, so that means 2x plus h squared minus x plus h plus 3, and then minus the 2x squared minus x plus 3. Okay, and then all of this over h. So that gives me 2x squared plus 2xh plus h squared minus x minus h plus 3 minus 2x squared plus x minus 3. All of this over h. So then I get 2x squared plus 4xh plus 2h squared minus x minus h plus 3 minus 2x squared plus x and minus 3 all over h. That and that cancel. This and this cancel. That and that cancel. So this gives me 4xh plus 2h squared minus h all over h. And this will simplify down into 4x plus 2h minus 1. And that is your final answer on the difference quotient. Okay. All right. That is section 2.2, more on functions and their graphs. So hopefully that wasn't too bad. Don't forget, if you have questions or anything, make sure you're sending me a reminder. Make sure you're sending me an email. And don't forget to hit that little button that says Ask Your Instructor. And don't forget, if you use that button, you must check your Dragon email. Alrighty then. It is late. I am tired. So I will see all of y'all when I see all of y'all. Have a good night, guys. TTFN. Ta-ta for now.